In this session, I'm going to talk about Apache Spark. So we're going to start off and go through some definitions. I'll follow that with an overview of the architecture of Spark, what the core concepts are, especially focusing on things that we need to know, which are transformations and actions. So what is Apache Spark? Apache Spark is an open source big data processing framework. It's built around speed, ease of use, and sophisticated analytics. In particular, it's written in a language called Scala, and it runs on Java virtual machines. So there are actually three interfaces for Spark, which are Java, Scala, and the one that we'll use, which is Python. So even though mostly we'll be using Python and Jupyter notebooks, you'll actually be doing something which runs on JVMs, and as part of the module software we have a Java virtual machine loaded. Originally the language environment was developed in 2009, open sourced in 2010 as an Apache project. It's still open source. There is a commercial company which was set up to exploit Spark. You will meet that quite a lot as it does run natively on Azure, and that is a company called Databricks. So you'll find that quite often Databricks have got useful documentation that you wouldn't necessarily find immediately. But the main Apache Spark website contains our material. So the project's goals were to essentially be compatible and improve on an earlier system. The earlier big data system is a system called Hadoop. You can read about Hadoop. It's not directly relevant to what we do. Hadoop was designed to allow processing of big data. That's data which doesn't fit into one machine, so works on many machines. But Hadoop was mostly disk based, and what that meant was even if you had a lot of memory, most of the computation was going on in disks and it was relatively slow. Also, if one of those machines where the data was distributed had a problem, it didn't cope particularly well. So Spark was designed to be fault tolerant. And the basic background is they expected fault to be the norm, something which happens all the time, not the exception. So for example, you go into any lab in the university halfway through the semester, and you'll find that one machine out of 30 isn't working for some reason. So if you multiply that problem by, let's suppose you have data which goes over 1,000 machines, there is always going to be some machine which is failing, or worse than failing, is going very slow. So Spark is designed to get around that by managing how the work is distributed, and it will allow for redundancy. Mostly we don't meet that. The architecture is very simple and it's easy to use, and that's why we're using it in this module. Let's go through some definitions now that will meet when you use the Spark documentation. First is cluster. Now we do meet the word cluster quite a lot in computer science. In AI we talk about data clustering and things like that, but in this particular case we mean collections of machines or nodes, which could be in the public cloud, they could be on premises. There are various kinds of cluster managers, and a Spark cluster is one on which Spark is installed. Now those clusters, we will be using generally the Spark's own local cluster manager, but there are products around designed to manage clusters, and Spark is compatible with those, and you'll read more about that in the official Spark documentation. So things that will meet are Spark workers, Spark master, you'll hear quite a lot about the Spark master, and the driver. So the Spark master is a Java virtual machine which acts as a manager for the cluster in a standalone environment. So basically we have application parts which are called workers. They register themselves with the master and the master distributes work to them. And it also acts as a manager for resources. It decides how many executor processes there are to launch and what workers will be attached to those. So this is really something that you should be aware of. There is the master program. The worker is one or more Java virtual machines which will be responding to and following actions for the Spark driver. So Spark applications, as we'll see, get decomposed into tasks. Fortunately, this is mostly invisible to us, but to understand what's going on with Spark, you should be aware that there are the different workers going on, so your code is not executed serially. It might look like it's executing serially, which is a good thing, but in practice different parts are being executed by different workers on different elements of the cluster, even if, as is more usual for us, the cluster is actually one machine which is multi-core. It's not necessarily like that. So the worker's job is to launch executors on behalf of the master and essentially will collect results. So the executor is actually a JVM, Java Virtual Machine Container. It has cores allocated to it and it has memory for executing certain tasks. Each worker node launches its own executor with some differing numbers of cores. So this is something that we would look, cores or threads actually, something that we look at when we're monitoring our Spark execution to see if the right number of cores are being used. So I've mentioned data already. One of the things that the execute will be doing will be storing and caching data partitions in its memory. So I mentioned already that Spark has a focus on memory operations because they're a lot faster than disk operations. The problem with doing that and storing intermediate results, of course, in caches is that you can quite easily exhaust that memory. And if you do that, then you've got a problem. So we have something that we'll look at later on in the module where you can get faster results by caching intermediate data. There is a specific instruction to do that, or not caching it in case you run out of memory. So this is part of optimization we look at in week 11. Most important of all is the Spark driver. Now at some point the driver, which distributes information, Spark tasks to the executors, it also gets computed results. Now if we're working with big data and we have more data that will fit on any one machine, then if you're not careful, communicating results back to the driver means you will run out of memory on the driver. This is called an OOM, or an out of memory error, and you see immediately when we're communicating results by the driver because that acts as a bottleneck in some of the computation. So we'll go on and we'll look at the architecture of Spark programs, but you need to bear in mind we've heard about the master, the driver, the workers and the executor, and this terminology gets used throughout. So we'll stop at that point.